Ready? Okay. Okay, so this figure is, this figure even has what is the amount of carbon in gas, oil, coal, right? And then it has this huge, ocean floor sediments that is almost equal to the amount of carbon in soil, right? And then let's see, this is dissolved organic carbon, and this is the deep ocean and intermediate. And this is exactly what I called in the previous lectures dissolved inorganic carbon. That is a summation of basically dissolved CO2, bicarbonate, carbonate, and carbonic acid. Right? Okay, I think what I would suggest is you take a look at this figure very, very carefully. And I think if you can understand each number on this figure thoroughly, for that, of course, you have to go back to the main text and read all the things. If you can, in fact, understand everything is on this figure, you pretty much know the global carbon cycle. Okay? Okay, now the major perturbations, as I showed in the previous figure, are this fossil fuel emission and land cover change. In fact, this was one of your quiz questions. So 10% of the today's anthropogenic emissions come from this kind of deforestation, and 90% is from fossil fuel emission. So, very nice round numbers for 2012 and 13, very close to the total is about 10 gigaton of carbon, 9 here and 1 from deforestation. Okay, so again, to reiterate that main important point, this is a carbon budget from the last decade. I mean, the year is 2003 to 2005. Okay, so these are really, very latest numbers. These do not come from a book. These are actually coming from actual continuous monitoring of the global carbon cycle. In fact, there is a program called Global Carbon Program. Their main job is to really monitor these fluxes every year. So they keep updating these numbers every year. So that's why it's really, if you look at the decade, it's the most recent decade. Okay? So anyway, if you look at this 8.6 here, 0.8, so 9.4 gigaton in the previous decade, and roughly 27% went into the ocean, 27% went into the land, and the remaining stayed in the atmosphere. So sometimes we call this as airport fraction of our emissions. So in this case, airport fraction is 0.45. 45% basically stays in the atmosphere. This is a very simple rule of thumb that nearly 50% of our emissions will stay in the atmosphere for at least in the near multiple decades. So in fact, here is the resource for that. So this is a paper published by Lacore, I think Biomedical Sciences, and this is a center in the US where they keep calculating the amount of fossil fuel that is actually used up each year. So this center provides that, and this is a project that was the Global Carbon Project. It basically collects all the information about global carbon fluxes and publishes it in the form of either a paper or a PowerPoint presentation each year. In fact, this slide is exactly from that particular program website. Okay, so all of you, of course, certainly know that where the majority of the carbon is, it is in the biosphere. In fact, I just want to see the biosphere contains roughly about 2,000 gigaton of carbon. And can you tell me how much is in the biomass and how much is the soils? We did discuss this in the last class. There was a schematic. Anyway, 500 gigaton is in the biomass, roughly 500 gigaton, and the remaining nearly 3/4 of that, 2,000, that is 1,500 gigaton, is in the soil. So the soil is actually the forest soil. They typically tend to have more carbon than the living biomass. Okay. All right. I think I want to actually a little bit talk about the difficulty over land. In general, getting this land up, I mean, for example, the 27% that in the previous thematic diagrams, I was showing you nearly 2.6 gigaton or 2.7 gigaton of carbon going into the land each year. How is that computed? In fact, it is one of the most difficult quantity in this particular figure. In this chart, it's actually easy to estimate this, it's easy to estimate this, and also it's easy to estimate this. The most difficult quantities are related to the land. Any reason why it is easy to do, estimate this flux over the ocean, but why it is difficult over land?
Because the area covered also like plants are different.
Anyway, the answer is here. The real problem is land is very heterogeneous. I think that is the reason. You look at this landscape here. There is a lake, there is a patch of grass, again a water body, then again some kind of grass. There is. So if you look at the land characteristic, it is so heterogeneous. On the other hand, you look at the ocean. If you go into the, if you go maybe 100 kilometers into the ocean, it's very homogeneous. I think I did emphasize this point. Homogeneous versus heterogeneous. So, if you want to estimate, let us say, the flux of carbon that goes into the ocean or the flux of carbon that comes out, if you make a single point measurement over the ocean, it could be representative for hundreds of kilometers surrounding that area. So, it is easy to have even few measurements and come out with a reasonably good estimate of the ocean numbers because it's homogeneous. So it's not difficult. But if you really want to do this, you really should be evaluating here, then what's happening here. So, but do we have that kind of measurements? In fact, if you go back to the third IPCC assessment, this also, there was a box which really explained why it is so difficult to get actually this land carbon flux estimate directly. It's almost impossible. So even today, how it is estimated? It is basically estimated as a residue. So what you do is you have an equation like this. That is, I can easily write like this. Let's say fossil fuel addition or anthropogenic emission. This goes into atmosphere plus ocean, right? Plus land. So all you do is we can estimate this because there is an institute that is estimating fossil fuel emission of CO2. That number is known to very good accuracy, and atmospheric CO2 measurements can tell you each year how much CO2 is increasing, and ocean also can be estimated fairly with the decent number of measurements and some ocean model estimates. So all we have to do is that land activities, F minus APM minus oceans. This is how it is estimated right now. So this is an important message you have to be aware of. That is, the land carbon fluxes are not directly estimated. So this is what is called a residual method, because every other term in that budget equation. This is like a budget equation, right? So in this budget equation, everything except the land. So land is indirectly derived. Don't think land estimate comes directly by some kind of measurements. Okay? Alright. So the reason is land carbon distribution is heterogeneous. So land carbon is normally estimated as residue. And if you really want to directly estimate land fluxes, you cannot do it today. And if you want to do it, you should have observations at least at a resolution of 1 kilometer. I mean, this is the estimate. At least you need observation at a scale of 1 kilometer, which I don't think we are going to have in the near future. But I think that maybe in the future, remote sensing may methods to calculate that. Okay, now what are the key issues that we have to consider under climate change and its relation to carbon uptake over land. There are three issues at least. One is longer growing season, particularly in the colder regions. For example, already it has been estimated that the growing season in cold countries has increased by about 2 weeks. So the cropping season could increase, or the time when photosynthetic activity can vigorously happen is increased by 2 weeks. So that means in the higher latitudes there is more carbon sequestration into the land. That's what I'm saying. So this is a good thing because in the high latitudes, photosynthesis can take place over a longer period in summer, right? And then there is another important thing that is called CO2 fertilization. I'm sure many of you must have heard that if the CO2 level in the atmosphere increases, photosynthesis can proceed faster. So the photosynthetic uptake of carbon can proceed faster. So the amount of carbon sequestered today is actually probably higher than the amount of carbon sequestered in the previous time. So these two factors are of course helping. And also there is, I'm sure some of you may be knowing, those who have done some biochemical cycles, that plants also need, in addition to carbon dioxide from air, they also need inorganic carbon and inorganic nitrogen to create amino acids and protein. So this is an important thing, and in fact, in the last few decades, there is an enormous amount of anthropogenically generated inorganic nitrogen that is actually the main source is, of course, fertilizer, for example. Fertilizer is actually not a natural thing. We humans have created this chemical, and because plants need them, we have put it. So this is supposed to also play a major role. So basically, it is believed that in the last, at least in the industrial era, these three things are happening, and they are all affecting and basically helping the terrestrial ecosystem to take probably more carbon per year. Is that clear qualitatively? Okay. Now, I think there is one more thing which is, which actually does not happen. That is what we call as respiration. Respiration is basically the decomposition of the plant matter, right? Now, in fact, this respiration is mainly a function of temperature. So warmer temperature means the decomposition can proceed faster. So in fact, if you look at, even this is a average sensitivity true, the tropical soils actually have less carbon than the soils in the high latitudes because it is cold in the high latitudes. So the decomposition, the bacteria cannot, break down the organic carbon. So the tropical soils actually have less carbon. Unfortunately, it's not very clear. So you can see this is microbial decomposition, and there is root respiration. So together, this decomposition and the root respiration, just like this. Where is the respiration here? Storage. Okay. Yeah, leaf and stem respiration. So that is called autotrophic respiration. That is living parts, doing respiration. So this is autotrophic respiration. In fact, this is also this is group respiration. That is also autotrophic part of autotrophic respiration, right? Anyway, if you look at the functional form, it can be represented by a simple form like this. That is, respiration purely depends on temperature. The Q10, so this is what we call as Q10 formulation for respiration. So you can see that if you use this relationship, the respiration will double for Q10 value of 2 for every 10 degree increase in temperature. So this is an important thing. So what it means is, as the temperature of the planet increases, plant respiration and soil respiration will go up. So this will actually not help sequestration, right? Because more carbon is actually going into the atmosphere. So this is the main negative, I would call it negative effect of global warming. That is, when the planet warms, the respiration of the ecosystem actually increases. Now, why this is important? Let's go back here. Yeah, okay. So, the high latitudes, in addition to the soil carbon that I gave as an estimate of 1500 gigaton, in addition to that, there is a lot of organic carbon buried in the soil in the high latitudes like Siberia or Alaska, where the soil temperature never goes above 0 degree. So that means absolutely this carbon is preserved there. It is not able to decompose because bacteria cannot, of course, work on this material. So, as climate warming proceeds, what's going to happen is some of these regions is going to, the temperature is going to be suitable for decomposition. So, this is in fact, 10 years back, this was created as a real big scare. In fact, still today, it is a valid feedback that's ready to happen. That is, there is a lot of soil in the polar region, the soil in the polar region that contains organic matter, and if global warming proceeds at a faster rate, this is additional carbon you are putting into the atmosphere. So this will really accelerate climate change. So the land, there are two competing processes. Like as I said, nitrogen deposition, CO2 fertilization, and the longer growing season in the high latitude. They can all help, so that the terrestrial ecosystem can be, sequester more carbon. But the permafrost, thawing, and enhanced plant respiration can act in the negative way. So it can accelerate climate change. Okay, now let's look at the ocean. What the ocean will do. Okay, now ocean. I think this is the summary slide. There are three key things you have to look at. Three key processes through which actually ocean controls the carbon cycle. One is the ocean chemistry. I think I showed you the relationships, equations last slide, and I will come back to that. And then of course ocean biology. This is basically phytoplankton. Just like land plants, of course in land we have trees and many types of species. But in the ocean, mainly it's the phytoplankton which do the photosynthesis. Okay, so in fact, it turns out the net primary productivity on land is about 60 gigaton of carbon per year. In the ocean, it's quite comparable. It is about 45 gigaton of carbon. That is net primary productivity in the ocean, and then ocean circulation. So we will come one by one to this discussion of this. So this is the ocean chemistry. So, as CO2 increases, let's look at this. So, CO2 first, it gets dissolved, and then it forms carbonic acid, and then one hydrogen group again can be dissociated. So, it produces bicarbonate ion, and then carbonate ion. So, these are all equilibrium reactions. So overall, of course, for the current pH, most of the carbon in the ocean is in this form. The inorganic carbon is the bicarbonate. Okay? 90% of the carbon is in bicarbonate. Now, this equation actually can be simplified. You all know when you have multiple equations, you have, I'm sure, how to summarize them into one single equation. So, this part is going to happen. For example, here, when you put CO2, this is the combined equation, the combined all those four equations. So basically, carbon dioxide dissolves in the ocean and it takes up the carbonate to produce two bicarbonate molecules. This is the crux of the ocean problem. So, what is the result is CO2 invasion into the ocean removes carbonate in the ocean. And carbonate is very important. Carbonate concentration should be higher in the ocean so that certain marine organisms, they can make the shells and skeletons. These are microorganisms. They need higher concentration of carbonate. So, this is the this equation is more and more. So as you put more and more CO2, this reaction will proceed in this forward direction. So it's going to reduce, it's going to basically take up carbonate that's already in the ocean. So addition of CO2 will deplete CO3 and buffering capacity, which means now the ocean is taking up CO2 not because it is just dissolving, right? It is because of this, because of basically carbonate ion that is available. So now, otherwise, for example, if carbonate ions are not there in the ocean, it is merely production of carbonic acid, that's it. So the ocean is right now taking more carbon dioxide because of this presence of carbonate ion in the ocean. Right? So this is what is called buffering capacity. Now, what is the meaning of buffering capacity? The number right now is 10. That is, the ocean is taking right now, the rate of the ocean can take nearly 10 times more carbon dioxide because of this presence of this. Now, if you reduce the carbonate ion, what's going to happen? Its buffering capacity is going to be reduced. Right? If you look at the previous equation, I think I didn't put the numbers, but if you really calculate the amount of carbon, I said here 90% is in the bicarbonate form. So that really another 9% is in this carbonate form. So only 1% is in the form of carbonic acid. So that means for every molecule of carbonic acid, the ocean right now contains nearly 10 carbonate ions. So that means the ocean's capacity, because of the presence of this carbonate ion, is 10 times. Now, if you reduce the carbonate ion, what's going to happen? Its buffering capacity will be reduced. So this is the problem. That means in the future, when the ocean is depleted of carbonate ion, it's going to take up less. Right? This is a serious issue. In fact, I think this is the single most important lesson we need to learn in ocean carbon cycle. Okay. Now, there is another factor called Raval factor, right? So, people used to think, for example, if you increase atmospheric CO2 concentration, let's say by 10%, people used to think, well, if you increase atmospheric CO2 by 10%, I'm sure you should be able to also increase the ocean carbon content by 10% because they are in equilibrium. Ocean and atmosphere are in equilibrium. So in equilibrium, if you increase this by 10%, you should be able to increase the other one also by 10%. But in reality, that's not going to happen. The ocean carbon content will increase by 1% because of this buffering. Right? Because when you have more CO2, the ocean will not be able to take up because it has less carbonate ion. So the Raval, this is because of this difference between 1% and 10%, it was called the Raval, it's called the Raval factor 10. Okay, now here is a good example to illustrate that. You can see the equilibrium concentrations at various pH and CO2 levels. So you can see that as CO2, where is CO2 here? Yeah, as CO2 increases, of course pH reduces, and you can see as CO2 goes up, carbonate comes down. I think this is a beautiful graph. If you remember this, you understand, I think, bulk of ocean, why is it related to ocean? I mean, related to carbon. Okay? So the carbonate, you can see how it quickly goes down. In fact, pH 6, it's pretty much, it's how many hours? 3 hours of 3 hours of magnitude smaller. Okay, so this is a large scale. Okay. So right now you can see this graph again. Right now the ocean water has about 8 pH, mostly. Yeah. Pardon me?
Explain the y-axis.
Y-axis is the ratio. I mean, these are just when you have completely acidic ocean, all the carbon in the ocean is only in the carbonic acid form. When you have very basic ocean, all the carbon is in the form of carbon. So, if you ask me this, so you need to, as long as you have basic ocean, it's good, right? Because you have lots and lots of carbonate, which is good for marine animals. Okay. Now, I think here is some explanation of some more information. So, as more and more CO2 gets dissolved, the buffering bar factors become small. The capacity of seawater to hold more CO2 declines. This is because not because it cannot dissolve, because it cannot now the CO3 is depleted, so that reaction cannot proceed. Okay. Now, so this is dissolved inorganic carbon increase is now smaller by 40% than for a similar increase. So if you increase the atmospheric CO2 concentration from today's level 380 to 480 ppm, it's going to be the DIC increase is going to be smaller by 40%, and it's going to be even dramatically smaller when CO2 goes from 750 to 850. Okay. So, this is a very serious concern, that is, the rate of ocean uptake in the future will decline. As far as our understanding of chemistry is concerned, I think that's what's going to happen. Okay, now, the next one is, okay, so that is related to the chemistry. There are three things going on in the ocean. One is chemistry, and this one is biology. Biology can also take, right? Phytoplankton, they have taken CO2. Right? Marine organisms take CO2 and just like the plants over time, they convert it into organic carbon. When these organisms die, some of these organisms can settle down to the ocean floor. Okay. So this is one way to also remove the current buildup of atmospheric CO2 because CO2 goes into the ocean, the plants can take. But the interesting thing about this is ocean ecosystems are not really CO2 limited. They already have, so the future increase in atmospheric CO2 is not going to really help this. But on the other hand, land plants are of course CO2 limited. That's why the photosynthesis can proceed faster over land under elevated CO2, but the ocean, Okay, so this implies removal of CO2 over land is mainly a biological process, but it is chemical and of course physical in the ocean. So it's going to be, biology is not going to help, I mean that's the message. Under higher CO2 concentration, you're not going to have more photosynthesis over the ocean because it is not limited to CO2. It is limited by other nutrients like iron, nitrogen, phosphorus. Okay? Alright. I think this is another important message. Many times people think, well, we can stimulate the ocean biology. But they are not really limited by this. If you really want to stimulate ocean biology, you have to go and add these nutrients like iron fertilization. I mean, there are proposals to actually dump iron into the ocean to increase this what you call this ocean fertilization. But I think I don't want to go into that. Let's just stick to our science here. Okay, now the next is circulation. So three things I listed. One is the ocean chemistry, ocean biology, and ocean circulation. So this is the ocean circulation. So if you look at the Atlantic cross section, so this is the South Pole, North Pole, and this is the meridional direction. So equator is something here. Yeah. So if you take the cross section, this is the schematic. So if you look at here, in Antarctica, in Atlantic, what is happening is cold water is taking the North Atlantic as well as the Antarctic region. So what happens is cold water flows from the high latitude surface into the deep ocean, right? It carries with it gases like CO2, right? So this is the way the circulation can actually take CO2 from the surface. If you recall, CO2 dissolves into the surface ocean. Now, this particular thing can happen only over high latitude because that's where water sinks, right? Only, see what you have to do is, if you want to go CO2, back in the first lecture itself, I told you that the carbon has to be taken to the deep ocean because once it's taken to the deep ocean, it may not come back for at least multiple centuries. So, this is the process actually that we really take it to the deep ocean. So the circulation is very important, but the trouble is the deep ocean ventilation takes many centuries. So this is not a fast process. So it cannot proceed faster. Okay? So removal of anthropogenic CO2 means it will take multiple centuries. I mean, by this process, if you rely on circulation, it's going to take a long time. Because this is not like the word you can picturize and go quickly going down. No. This proceeds as a very, very long time scale. Because if you recall, the ocean vertical circulations are very slow. One way to get the time scale is, for example, for this water, for example, if you make the loop like this, it will take multiple centuries. So that's the problem. So whether what so it means is whatever CO2 that we are putting out, it's going to at least stay in the atmosphere for a while. Because this is one process that can really take to the deep ocean. But the unfortunate thing is this is not a fast time scale process. Okay? So another interesting way to look at that is what we call old waters. Why when it goes to deep ocean it is good? The reason is, let us say today I am here. Today there is some water here. Now you consider another water sample here. Okay? You take a water sample here. Now, when do you think that water parcel might have been on the surface? Just thinking about the simple multiple century time scale, this water parcel in this point, it might have been at the surface probably 200 years ago, because it takes 200 years to come to that level. So that means if it was here 200 years back, it might have come here today. Now, you think about this water parcel also eventually will come back to the surface one day. Right? So it may be another 200 years, it might come back. Right? It's possible. I mean, that's the speed with which these things are proceeding. So if you use that analogy, now you think about some water parcel here. Suppose that water parcel saw the atmosphere about in the pre-industrial time. Now what was the CO2 in the pre-industrial time? It was 280 ppm or somewhere between 200 to 280 ppm. Now this water here at the surface, now it is seeing an atmosphere of 400 ppm. So it's getting saturated by a 400 ppm CO2. But the water here is saturated with only 280 ppm. So when this water comes up, it can take up more carbon, right? Because it was saturated at only 280 ppm. Now the atmosphere is at a higher CO2 concentration. So that is why when deep ocean comes back to the surface, it has the potential to take up more CO2. So I think that's what I have written here. Deep water that was exposed to the atmosphere many centuries back is brought to surface by this thermodynamic circulation. Now these old waters, where waters eventually take new atmospheric CO2 because they are not equilibrated with current CO2. They were equilibrated with lower concentration of CO2, so they can take more CO2. So since old waters take centuries to come back to surface, the time scale for this type of CO2 removal is multiple centuries. Okay, now I have some, I think, at least interesting things to show to you. That is ocean acidification. CO2 is corrosive to the shells and skeletons of marine organisms, that we know, because I think I have already actually talked about why this can proceed, because you saw the pH plot as well as how the concentration of bicarbonate, carbonate, and carbonic acid vary with pH. Now let's look at so these are these are coral and these are there are many types of planktons, and these are called calcareous plankton. So they basically need I think the rough rule is they have to be the calcium carbonate saturation in the water has to be at least 2. Saturation fraction is 1. So you need to actually have nearly 200% saturation of, that's a kind of general, then these marine organisms won't have problem building the shells and skeletons. Okay? Now, let's look at, just very nice animations here. So, calcium carbonate in water. So, we have water, and let's say, I said acidic ocean is corrosive to marine animals. Okay, basically, what I mean is corrosive to this. You have this calcium carbonate. Now, you can actually knock this out, right? So, how that happens? Let's look at that. CO2 first, CO2 comes in. The previous figure you had only ocean water and the calcium carbonate. Now CO2 comes in, and that's going to form, let's say, dissolved CO2, H2O liquid, and it forms carbonic acid. So, H2O combined with CO2 forms the carbonic acid. Now you see what happens. Something is really weird. Okay, now one of the hydrogen ion gets disassociated. So you form bicarbonate and separate the hydrogen. It comes and it actually knocks down. So you basically create another bicarbonate. So this is what happens. That is, calcium carbonate basically dissolves. So basically you create, CO2 dissolving in water. It basically, the end product is, it knocks out the calcium and the calcium carbonate, and you get 2 bicarbonate. So this happens because of the new pH, right? Everything depends on the eventually pH level. Okay, same reaction I think is repeated now. I think, okay, again, H2O, just for your understanding, again, just to repeat it, CO2 comes in, it reacts with water to form carbonic acid, a hydrogen ion comes out, and it knocks out calcium. So, I think when you put more and more CO2, the basic message is, because the pH actually goes down, the calcium basically comes out. Okay. All right. So the simple message is, so that is basically what I would call as, I think the simple, I think whatever ocean biology and chemistry I have described today, that also explain the ocean acidification process, right? Okay, here there are some very scary calculations. Okay, let's go through this slowly. So this is a projection for year 2100, and this is a projection for the bottom two panels are projection for 2300. Okay, so these are the pH values in this side, and this is what is called the saturation with respect to calcium. There are 2 types of calcium carbonate. One is calcite. This is easily dissolvable, and I think this is easily dissolvable. Okay. Now, if you look at this very carefully, this is the pre-industrial level of pH in the ocean. So this is south pole, north pole. 60 degrees now. So even pH has a distribution. Don't think the entire ocean has to be uniform. Okay. It has, you can see this nice distribution. Right now, the pH, north is actually much higher. Now, you look at what happens. So this is the pH level in year 2000. So in year 2000, we have already reduced the pH of the ocean so far. Under current conditions, the ocean pH has gone down by 0.1 from 8.2 to 8.1 now. And these are some future projection scenarios. So for example, B1 is a low, very low amount of carbon emission, and A2 is very high amount of carbon emission. You can see the pH of the ocean by 2100, it will go down to 7.7 from the current 8.2. Now, this is by year 2300. If you emit various amounts of fossil fuel emissions, like this is 1250 petagram, 2500 petagram of carbon. I mean, okay. So currently we are emitting about 10. Okay. Suppose our emission rate becomes 25 petagram of carbon per year. So this emission rate will take place over 180. So these are not, unrealistic scenarios. These are, for example, these two at least up to 5,000 gigaton. They are plausible scenarios. So if you look at that, pH can go down for 5,000 gigaton of emission, it can go down to 7.4. And if you, of course, these are probably unrealistic amount of carbon emissions for a year. Now, look at the saturation ratios here. Interestingly, high latitude ocean is the one that is, in terms of saturation, it already has a lower saturation compared to this area. So, have you ever wondered why corals are not found in the high latitude? Corals are mostly found only in the tropical and subtropical water. That's because you can see the saturation ratio is very high. So they can build the shells and skeletons only when the water is highly saturated with carbonate matter. Okay, so these are the tropical regions are the regions where the saturation is high. But you can see for V1 scenario, we do actually go below 2. So the high latitude marine organisms, according to this model result, will have a problem by 2020. If anything below 2, they will have it. Even though one might think 1 is enough, but I think 2 is the optimal. Below that, it's not good. So, in the high latitude, particularly in the southern ocean, marine organisms will face problem by year 2020. And the situation, of course, gets really worse for even for it actually reaches 1 or 2,500 carbon. Anything beyond that, is actually dangerous for corals for various emissions. For example, let's see here, 2 is optimum. So I think corals definitely could have a problem after 2,500 petagram of carbon. To give a context, anybody knows how much amount of carbon we have emitted to the atmosphere so far since pre-industrial time? How much? 800 megaton.
So 1 ppm is
1 ppm is equal to 2 gigaton. So you might easily calculate backward like that, right? 50% are staying in the atmosphere. That means now the increase is 100 ppm. So obviously another 50% has gone into the ocean and land. So that means we must have emitted at least 200 ppm, right? 200 ppm is equal to close to 400 gigaton of carbon. So the exact figure is actually a little more complicated, but because of the land emissions, particularly deforestation, that is also put into this carbon emissions. But anyway, the actual number is 560 gigaton of carbon we have emitted so far. So to give you an idea, even if you want to go somewhere here, we still have approximately nearly 50% emission we can do. If you think we will take this particular route, that is 1250 petagram of carbon emission by year 2300. Okay. So I think that's kind of ocean carbon cycle and how it will be perturbed in the future. Okay. Now I think I just want to cover a very basic concept which involves also the land, ocean, and the geological cycle. So for that, let's say on a long term, there is a possibility that we may release all the conventional fossil fuels, that is about 5,000 gigaton. So that is somewhere, if you look at this previous plot, So 5,000 gigaton means this one here. So which is a very scary scenario, because many regions the saturation does go below 2, okay? And in terms of only pH can go down to 7.4 by year 2300. Now, the question is very simple. You are putting 5,000 gigaton of carbon into the atmosphere. Where it will go? 5,000. 5,000 is a big number. So far we have emitted only 500 gigaton, right? If you really put too much carbon dioxide into the atmosphere, which can happen over long term, maybe not in the next 10 years, but in the next 200, 300 years, we may be doing, if we are doing it today, we are doing right now. So, land cannot take a lot because the size of the reservoir itself is only 2,000 gigaton, right? The reservoir size itself is only 2,000 gigaton. So, how big you can make the reservoir big? Further, we are also, if the planet warms, whatever carbon that is stored in the high latitude will be actually coming out. So, land may not have much role in taking up carbon in the future. That's a very simple message. By just looking at these numbers, if you put too much carbon, like 5,000 gigaton of carbon, land cannot take it, right? Because land, its capacity, its total amount itself, what we know is only 2,000. So even if you increase by 10% or 20%, even 20% we can increase, let's say, by whatever means we do, that will still amount to only, you can take up 1/10 of the emission, right? 5,000 gigaton of carbon. So if you increase the land capacity by 20%, it will give you about 400 gigaton of carbon. So that's about less than 1/10 of that. So where it will go? So if you get it down too much CO2 into the atmosphere, where it will go? So let us see who is going to really take this up. Okay, so land role is very limited, as I had shown you. So I think next box we can check this ocean. Well, we go and ask ocean, can you take it? Right? Okay, so what's the ocean going to tell? Let's say CO2 emission is going to, of course, acidify the ocean, right? Carbonate ion concentration is going to decline because of that. Now, acidification is going to, of course, dissolve shells and skeletons of certain marine organisms. Now, the problem is the ocean will become so much acidic. Right now, if you know, the ocean also has sediments, carbonate sediments. The shells will be dropped, right? Now, if the acidification is too much, I showed you a nice animation, how calcium ion could be knocked out from calcium carbonate. Now, that means it could even dissolve the calcium carbonate on the ocean floor. It's not only the marine animals, but it could also dissolve that. Now, I think, so basically ocean pH is lower. That is why this all happens, can all happen. But I'm sure you all heard about Le-Chatelier's principle, right? Le-Chatelier's principle for equilibrium reaction. Now what's going to happen is, as you dissolve the ocean floor, I didn't really show this reaction, but I think I showed you this reaction, right? This way I showed CO2, H2O, CaCO3. This is what I showed in the animation. It proceeded this way and it was producing a calcium ion and 2 bicarbonate ion. That's what it produces. Now, if you dissolve the skeletons and shells of the marine animals as well as the sediments on the ocean floor, what is the net result? You are actually producing more and more of this, right? Now, once this concentration increases sufficiently enough, the reaction will just proceed this way too, right? And also, so in this process, remember these reactions are all equilibrium reactions. So they will be going back and forth. If concentration of concentration on this side exceeds certain amount is going to go this way. Now you look at this way, this reaction is now producing CO2 instead of taking CO2, it's producing CO2. So that means this CO2 will be released to the atmosphere. So now, once the ocean has become sufficiently acidified, right? Acidification happened because CO2 was being taken by the ocean. But this acidification itself eventually, after reaching too much acidification, it might the reaction make this revert this way, and it will release CO2 to the atmosphere and pH will increase. pH will increase because you are releasing CO2. Now, increase in atmospheric CO2 would of course lead to that again. But again, remember, so this is going to be back and forth reaction, right? I mean, it goes up, pH will go down, and then it can go up, go down. I mean, so you are going to have a long time scale process where CO2 for a certain period will be taken up from the atmosphere by the ocean, and then you are going to have another type of equilibrium where CO2 will be released to the atmosphere. So you are going to have an oscillating cycle, and which could have thousands of years, right? Now, okay, back and forth of increase and decrease of pH, this process will take thousands of years. So eventually, there is ocean has the potential to take lot of CO2 that we are emitting, but the only problem is see the time scale. Okay? So I think if at all you take a message from today, it's not that climate change problem is not solvable, it's just too long. If you let nature to do its job, it's going to eventually remove. We will go back to pre-industrial CO2 concentration levels. But before that, we are going to damage a lot, right? Okay, I think there is a nice, result from this new IPCC. I think it's actually very nice. If you look at this, okay, so this blue shows the instantaneous emission of 100 petagram of carbon, as opposed to 5,000 as showed before. So you can see in the case of 100 petagram of carbon, nearly within 100 years, land and ocean can remove nearly 60% of the carbon. So if I put a pulse of today, let's say, huge amount of carbon I throw, that is equal to 10 years of emission, let's say. 10 years of emission, I do instantaneously today. What's going to happen is within 100 years, nearly 60% of the carbon will be taken up by land and ocean. Because 100 petagram of carbon is small, so land can play a huge role here. Okay? Now, if you, of course, there is still time. So if you allow 1,000 years, you can see that another 20% will be removed by the oceans. So, in about 1,000 years time scale, nearly 80% of the carbon will be taken up by land and ocean. I mean, this is for small emissions. But if you do large emissions, like here, this is for 1,000 petagram of carbon emission, and this is for 5,000 petagram of carbon emission. So here what is considered in this plot is only the role of land and ocean. So if you allow only land and ocean, after 10,000 years, still, even in the small emission case, still about 50% is left this atmosphere. So what's going on? So even for a small pulse, in the case of bigger pulse, nearly 20% of the CO2 stays in the atmosphere even after 10,000 years. I think this is a problem with CO2 emission. The CO2 that we are putting into the atmosphere today, it's really going to have long-term impact. And also, it's not completely removed even on a 10,000 year time scale. Even on a 10,000 year time scale, nearly 20% of the CO2 actually will remain in the atmosphere. So when it will really go back to zero here? So who is needed here to remove that remaining 10 or 20%? right? Well, nature will do it on time scale of hundreds of thousands of years. The silicate weathering will remove it, of course. I mean, I think we did talk about this. So, I think this should at least illustrate the long-term consequences of our fossil regulations. Right? I mean, in some sense, if you look at the history of that, we are having our own footprint. If you look at you brought time versus the effect of various things. There is a period starting with industrialization where humans provided a huge predation on the carbon cycle of the earth, which persisted for 10,000 years or so. Unless we do something artificial to remove that CO2, if you only rely on nature, the CO2 problem is at least a 10,000 year problem. Okay? Alright, I think I will stop here. Okay, there is one more slide, I think. Yeah, I think this is again, some of this same amount of carbon emissions. How much carbon dioxide actually in the atmosphere will, we are understanding either temperature or carbon dioxide level much more clearly than other things. So, this is for atmospheric CO2. So, if you do a 5,000 gigaton of carbon, you could reach CO2 levels of very close to 2,000 ppm. Today's level is 4,400 ppm, right? So you can maybe the concentration could become 5-fold for 5,000 kilogram of carbon, and the warming could be close to 3 to 4 degrees. Now remember, these are from simple models, and depending on in fact, there are two scales given here. This is if the climate system has a higher climate sensitivity, and this is for the lower climate sensitivity. For every doubling of atmospheric CO2, if the climate system warms by 1.5 degrees, the eventual warming could be about 3 degrees. But if the reason they have covered this range is right now for a doubling of atmospheric CO2 concentration, the range given in the IISc report is anywhere from 1.5 to 4.5 degrees warming. So if you go on the higher climate sensitivity side, the planet could experience already the emissions very close to 9 degrees warming by year, anywhere between 20 to 100, and CO2 concentrations, of course. But humongous emissions, like 20,000, you get another carbon, CO2 value. I mean, you could be really breathing bad air. Well, I'm sure we are not going to that. I think most likely somewhere between 1250 and 2500. I hope so. Okay. I think that's all I have. So if you have any question, we may have 5 minutes. Okay. So tomorrow is the morning. We have 2 lectures on monsoons, and the afternoon I'm going to hear what you have to say. Okay. All right. We'll stop here.
I kept all the speakers there.
No, okay. I think it's here.
Okay.